Page 168, picking up with lesson 3.2. We talked about yesterday on number 4 how many party hats and how many weeks it was. So 0, 300, they're starting out with 300 party hats, and then this is going down by 50 party hats each week. And like we said, you could technically argue probably that we can connect these dots because it's possible, you know, like part way through the week we would maybe have in between amount of hats. We could even extend this as long as we stay in the first quadrant. We don't want to have negative party hats or negative weeks. So if you look at number 5, how can Darlene use the graph above to know when to order more party hats? Well, a couple things there. Depends that she may want to look at this and say, something like, after 5 weeks, she only has 50 hats and should reorder. Reorder maybe. Okay, now that's going to depend on how long it takes for the order to actually come in. Because you can see from the graph here also, it looks like it's projected after 6 weeks we're not going to have any hats left. So that only gives us 1 week for these hats to come in. If it's going to take a couple weeks or 3, 4 weeks to get hats in, we would actually want to order them sooner than that. Workbook page 41 to look at a few more problems here. The first part is asking us to explain whether the graph represents a function. So like we talked about yesterday, what we're going to be doing here is we can draw some vertical lines. When we draw vertical lines, if we're hitting either nothing or just 1 point, we're okay, we have a function. If we're hitting more than 2 points or more than 1 point with our vertical lines, we do not have a function. So if you look at this one, would this be a function or not? Yes. Yes, good. We draw vertical lines here. I'm going to make red lines, I guess, so it's distinguished from the graph a little bit more there. Okay, and you can see some of these, there's nothing there, doesn't hit anything, but some of them, if it does hit anything, it only hits 1 point. And again, that's like we talked about before. That means that for an x value, we only have one y value, so that would be a function. Okay, and if you guys can just visualize the vertical lines, I'm not going to say you necessarily have to draw each one out, although you might find that helpful. Okay, number 2. No, why not? Good. So we're okay starting out. Okay, okay, not okay. Okay, so right here you can see that's crossing through -4, 6 and -4, -4. That's like our same ingredients making cookies and meatloaf. So that is not a function. Number 3, Marcus records the total number of calories burned after each mile he walks. So you can see that in the table. First thing is they want us to graph the ordered pairs. And they've specified on their table which one is the X and which one's the Y. So 197 is going to be our first point. So somewhere in between here. Then our next point, we've got 194. And we've got 291. So those would be the points. And then the question they're asking is whether this is a function. So based off what we did on the first couple problems there, is this a function?
Yeah.
Yes, good. Okay, now this one, it says to explain. So one way of explaining this, you could say yes, it passes the vertical line test. That's where we draw our vertical lines. It's only passing them, either nothing's there, or it's only passing through those one time. That's one way of explaining that. Another way, you could say, for each x value, we only have one y value. Or for a certain number of miles walked, he's only burning a certain number of calories. Okay? If he walked 1 mile, he's burning 97 calories, not 97 or 2,000. Number 4, the relationship between the amount of powdered fertilizer X needed to make Y gallons of liquid fertilizer is shown in the table. Is the relation a function? Use the graph to support your answer. Okay, so we already did these a little bit by not having a graph. If we have the graph, we can just do that by doing our vertical line test again. So we're starting out 0, 0, 6, 4. Remember X and then Y, 6, 4, 12, 8, and 18, 12. Okay, so just looking at those points that we've got graphed there, is this going to be a function? Yes, good. Okay, so we'd say yes, it would be a function. Again, you could just say it passes the vertical line test would be fine. Now, a follow-up question they could do, they didn't do it here. They could ask us whether this appears to be a linear function. Remember, a linear function is if the points follow in a line, in a straight line. So does this look like a linear function? Yes. Makes sense. Okay, if we're mixing stuff together, if we want it to have the same consistency, we need it to be proportional, we need it to be a linear function. Number 5, Robert swims a lap in the pool. His coach graphs his distance from the starting block. Determine whether each graph is a function. Justify your answer. So we can do again on these, we could just draw some vertical lines here to see whether these are going to be functions or not. So for the first graph, yes, good. So the first one would be yes. Again, it passes the vertical line test is a valid explanation, or we could just say, for every x we have a certain y value. For the second one, Yes, good. Okay, this one's maybe a little bit closer call. We got a little bit of curve to it, but again, if we draw vertical lines, it's only hitting the graph in one spot, so that would be yes as well. And for the last one, no, good. Last one is no. We've got all kinds of problems here. Most places we draw lines, it's going to hit twice. So we could say it does not pass the vertical line test. Okay, so then part B, it says which graph must be incorrect. Well, if it's a function, if we think about what that's saying for this problem, it's saying at a certain time, he is a certain distance from the start. So at a certain time, he's only going to be one distance from the start. With this last graph, it's like saying, you know, after 5 seconds, he was 2 different distances from the start. Well, he didn't split into 2 different places. You know, we can't be 2 places at once here, so that's not going to work. So this last graph would be the one that would be incorrect. We can't have 2 different distances from the start at the same time. Number 6 is asking which of these tables represent a nonlinear function. So nonlinear means it's not a straight line. So if we look at table 1, what we would want to do, probably the easiest way to tell if this is linear or nonlinear would be to graph the points. So input is like our x and output is like our y. So we graph the points here. We've got 3, 1, 6, 4, 9, 9, 16, 12, 16. And sometimes it's hard to tell at first, but as we get more points, we might be able to detect this. 15 and 25 is going to be up here off the chart somewhere. Okay, so if I think of connecting these points, and I know I'm not drawing necessarily perfect lines anyway, but does this look like this is a straight line? No. Okay, this is not a straight line, so this would be nonlinear. So that would be one of our answers. Okay, we could do the same thing for the next one here. So the next one we've got 219. Four, 9, 6, -1, 8, -11, 10, -21. Okay, so that'll be off my graph here again a little bit. So does that look better?
Yes.
Yes, so that one would be linear for table 2. Table 3, same idea, we can graph those, and what's going to happen is that's not going to be a straight line either. So table 1 and table 3 would be the ones that would be in nonlinear functions there. Another way you can tell that without graphing them is if they're increasing, like in table 1, our x's are increasing by 3 each time. If the x's increase by the same amount each time, the y's should also be increasing by the same amount each time, or decreasing, whatever. So y is increased by 3, increased by 5, increased by 7, increased by 9. It's a pattern, but it's not doing the same exact thing each time. Okay, and the reason we know that that's going to be nonlinear is, remember, we talked about slope is change in y over change in x. If we have a straight line, our slope is the same at any 2 points on the line. If it's nonlinear, that means, you know, here to here, it's this slope, now it changed, now it changed. Okay, so table 2, the x's go up by 2 each time, and the y's go down by 10 each time. So it's doing the same thing every time. Change in y divided by change in x, that means our slope anywhere on that graph is -5, so that means that's a straight line. And again, we could do the same thing on the last one, and that is got some major big and small numbers there, is why I didn't graph that one, but that one is nowhere near to being a straight line either, so that's nonlinear. Number 7, Greta opens a savings account with $25. She saves $20 each week. The table represents her account balance. Write a function that relates the amount of money in Greta's account M to the number of weeks W. So you can see the 0.25, that's representing that she started with $25 in there. And then after a week, she added $20. After a week, she added $20, and so on. Okay, so part A, they want us to write a function. If you look at your chart here, it doesn't always have to be like this, but usually if they've got it horizontal, what's on top is like your x and what's on bottom is like your y. So also what's the y is what we want to see a change in. We want to see the change in how much money is in the account here. So our money in the account M is going to be like our y. So normally we had like a y equals mx plus b. This one, a little confusing because we've got an m instead of our y. Kind of complicating things here. So maybe if you wanted to, we could do a slight variation on that. Maybe do a capital M instead of a lowercase m, just so we can distinguish our money from our slope. And then instead of the X, we have the weeks, which is like a W. So we've got kind of like a capital M equals MW plus B. Kind of a different look there. So what we could do, we could think about, like we've done before, is what is our slope, or what's our rate of change for the savings account here? How much is the savings account changing by? 20, yeah. It's changing by 20, so 20 is going to be like our slope. And we can think of this, you don't have to think of it this way, but this is just relating it to what you guys have done. $20 times how many weeks? That would tell us part of this. And then plus what? Right, plus 25 she started with. That's our y-intercept. That's our starting amount. So $20 times how many weeks plus the 25 would be the function. And then the question is whether it's linear or nonlinear. And this would be linear, right? Okay, and we could say for this one, we could say linear because it goes up $20 every week. Okay, it's a constant rate of change or a constant slope here. We start at a point, we go up 20 over 1, up 20 over 1, up 20 over 1. Okay, now it's not starting at 0, 0, so it's not proportional, but it is linear. It's still a straight line. Okay. What we're going to do for this then, page 169, numbers 6 through 14.